Hello, good morning. Unit 3, Electrochemistry, under Physical Chemistry, BSc second year, Institute of Science and Technology, Tribhuvan University. First of all, electrochemistry, the branch of chemistry which deals with the relationship between electrical energy and chemical interconversion of one form into another form is called electrochemistry. Or it is defined as the branch of chemistry that examines the phenomena resulting from combined chemical and electrical effects. Electrolytic conductance, it is defined as the flow of electricity through an electrolytic conductor. The electrolytic conductor is a conductor through which the electricity passes in the form of ions. The electrolytic conductance are following types: specific conductance. The conductance of 1 cm cube of a solution of an electrolyte is called specific conductance and denoted by K. K equal to 1 over rho. We know that R equal to rho L by A. So rho equal to R over L. I can again simplify. So substituting the value of rho, R equal to 1 over R A by L. Again solving L over RA. L length centimeter, R ohm, area cm squared. So unit per ohm per cm. Resistance, L length, A area, group constant, that is specific resistance. So unit per ohm per cm. Equivalent conductance, it is defined as the conductance of electrolyte solution containing 1 gram equivalent of solute placed between two parallel electrodes 1 centimeter apart. And the electrodes is large enough to enclose whole volume of the solution. Lambda EQ, K into V, K specific conductance, the volume of solution in cc containing 1 gram equivalent of electrolyte. If 1000 cc of solution contains n gram equivalent of the solute, the volume of the solution B equal to 1000 cc over n, so that lambda eq equal to 1000 over n into K, the unit per ohm per cm per equivalent. Molar conductance, it is defined as the conductance of solution containing 1 gram mole of the solute placed between two parallel electrodes 1 cm apart, and the electrode is large enough to enclose whole volume of the solution. Lambda m equal to K into V, K specific conductance, the volume of the solution in cc containing 1 mole of electrolyte equal to 1000 over m per ohm per cm per mole. Specific conductance decrease and equivalent conductance increase with dilution of a solution of electrolyte. Specific conductivity of a solution is the conductance due to all the ions present in 1 cm cube of the solution. As the solution is diluted, the number of ions per centimeter cube decreases, so the specific conductivity decreases with dilution. In case of weak electrolyte, the degree of ionization increases with dilution, and thereby total number of ions present in the whole solution increases. But this increase will be far less than the decrease in the density of ions due to dilution. Therefore, Net result is decrease in specific conductivity of solution for strong electrolytes as well as weak electrolytes. In case of strong electrolytes, there is an increase in equivalent conductivity with dilution, but the increase in mass less than in case of weak electrolytes. Strong electrolytes dissociates almost completely at any reasonable concentration of solution. Therefore, as the concentration of the solution is decreases, there is hardly an increase in number of ions, but the mobility of the ions increase due to decrease in the interionic attraction. Therefore, equivalent or molar conductivity increases. This interionic attraction decreases as the solution gets diluted, and thereby speed of ions increases, leads to the increase of equivalent conductivity. According to Dewey and Huckel, according to Dewey and Huckel, this the relation between the molar conductivity lambda C or lambda by m be the molar conductivity of equivalent conductivity at concentration. Lambda naught be the equivalent conductivity of infinite dilution. C concentration of solution. A and B are constant. The value of equivalent conductance is increases with dilution for strong electrolytes. The increase in equivalent conductance due to decrease in the equivalent force of attraction between opposite charges with increase in dilution. Decrease in concentration but not due to increase in number of ions. At higher concentration, the force of attraction between opposite ion increase and speed of ions with which they move toward opposite charge electrodes decreases. Hence, at higher concentration, equivalent conductivity decreases but increases with increasing dilution. But in case of weak electrolytes, the interionic force is negligible. So speed of ions not affected with increase in dilution, and also number of current carrying particles increases, which leads to increase in equivalent conductance. Coulom's law of independent migration, it states that the molar conductivity of an ion electrolyte at infinite dilution is the sum of the ionic conductivities of cations and anions is multiplied with the number of ions present on formula of electrolyte. Molar conductivity at infinite Ax By. Molar conductivity of the electrolyte at infinite dilution. Lambda A plus m, molar conductivity of cation at infinite dilution. Lambda B minus m, molar conductivity of anion at infinite dilution. For example, barium chloride. Coulom's law is also defined in terms of equivalent conductivities. The equivalent conductivity of electrolyte at infinite dilution is the sum of the equivalent conductivity of cations and anions that are migrated at opposite electrodes. Equivalent conductivity of electrolyte at infinite dilution. Equivalent conductivity of cation at infinite dilution. Application of Kohlrausch's law, it is used in calculation of molar conductivity and equivalent conductivity at infinite dilution, ionic conductance and ionic mobility. Ionic mobility is the drift speed acquired by ions per unit applied electric field and denoted by mu. The velocity of anion in cm per second under potential gradient of volume per cm is called ionic mobility. Ionic conductance, it is the ability of the given ion to conduct electric charge. Ionic conductance proportional ionic mobility. So we can write for anion and cation, lambda A proportional mu anion, lambda C proportional mu cation. So we can write equation 1 and 2. K equal to 96500 column. So equation 3. Where lambda A, mu A, lambda C, mu C are the ionic mobility and equivalent conductance of cations and anions respectively. From equation 3 and 4, we get mu C over mu A equal to lambda A 5, but lambda C, lambda A equal to T plus over 1 minus T plus 6. From equation 5 and 6, we can write mu C over mu A equal to T plus over 1 minus T plus equation 7, T plus transport number of cation. Conductivity of water. The conductivity of water is a measure of the capability of water to pass electrical flow. This ability directly depends on the concentration of conductive ions in the water. These conductive ions originated due to inorganic materials such as chlorides, alkalis, carbonates, and sulfide compounds and dissolved salts. Distilled water has conducting power due to presence of H plus, OH minus, and carbon dioxide gas. For more accurate work, the conductance due to water should be expected to be as low as possible with respect to the conductance of solution. For this purpose, water of negligible conductivity, example distilled water, conductivity water is used for precise lab work. For more accurate work conductivity, water is used. This conductance is mainly due to dissolved carbon dioxide gas from air. This type of water is called equilibrium water. Conductivity of water prepared, water is prepared by many time distillation. Of distilled water having a small amount of potassium permanganate and potassium hydroxide. The conductivities of different types of water, seawater, 5 cm per meter, drinking water, distilled water, conductivity water, deionized water or ultra pure water. Drinking water 5 into 10 to the power minus 3 cm per meter, distilled water less than 1.1 10 to the power minus 3 cm per meter. Conductivity of water 18 to 10 to the power minus 5 cm per meter. Deionized water or ultra pure water 5.5 into 10 to the power minus 6 cm per meter. Transport number. The fraction of current carried by a cation in an anion in solution is called transport number or transference number or returns number. Transport number of cation T plus current carried by the cation over total current passing through the solution. So T plus equal to I plus over I. Transport number of anion T minus, current carried by anion over total current passing through the solution. Transport number in terms of mobility. Ionic mobility is the velocity of ions per unit potential gradient. The quantity of electricity carried by ith species of ions through a solution is proportional to concentration of charge. So proportional to charge of ions and proportional of charge of mobility of charge of ions. The quantity of electricity Qi is proportional to concentration of charge Ci, charge of ion Zi, mobility of ions μi. Mathematically, Qi proportional Ci, Zi, μi. K is the proportionality constant. Total electricity carried by all ions is the sum of all of the Qi terms. Let total electricity Q equal to summation Qi. So K C1 Z1 mu1 plus K C2 Z2 mu2. So Q equal to K summation Ci Zi mu I. Fraction of total current Ti current by the ith ions Ti equal to Qi over Q. In the concentration of a single electrolyte producing two types of ions, cations and anions, by the corresponding transport number are given by T plus, T minus. For any electrolyte, C plus C Z minus equal to C minus Z minus, which represent the equivalent concentration of ions. So T plus equal to mu plus over mu plus plus mu minus. Similarly, T minus equal to mu minus over mu plus plus mu minus. Adding equation 8 and 9, T plus and T minus will get 1. It shows that sum of the transport number is always 1. Transport number in terms of equivalent ionic conductance, let lambda plus equivalent ionic conductance of cation, lambda minus equivalent ionic conductance of anion. Lambda equivalent conductance of solution, so lambda equal to lambda plus, lambda minus. We also know that the mobility of ion mu is directly proportional to the conductance of lambda of the ion at that concentration. Mu plus proportional lambda plus, so mu plus equal to k lambda plus, mu minus proportional lambda minus, mu minus proportional k lambda minus. Now mu plus plus mu minus, adding k lambda plus k lambda minus and common k lambda plus lambda minus. Now putting the value of mu plus from equation 11 and mu minus from equation 12, we get in equation 8. So T plus equal to k lambda plus over k lambda plus k lambda minus. Similarly, solving we get T plus equal to lambda plus over lambda. Now putting the value of mu plus from 11 and mu minus from 12, T minus equal to lambda minus over lambda plus lambda minus. That is the T minus equal to lambda minus over lambda. Lambda minus, lambda plus, and lambda are the equivalent conductance of cations, anions, and electrolyte at a particular concentration. In terms of coding, T plus equal to I plus over I, T minus, I minus over I. In terms of mobility, mu plus over mu plus, mu minus, T minus equal mu minus over mu plus. plus mu minus. In terms of conductance, T plus equal to lambda plus over lambda. T minus equal to lambda minus over lambda. So we can calculate transport number of cation anion in terms of current, mobility, and conductance. Retort's rule, it is based on the fact that during the electrolysis, the loss in the amount of electrolyte around any electrode is directly proportional to the speed of ion moving away from it. Let the migration of velocity of cation mu, migration velocity of anion B, transport number of cation T plus, transport number of anion T minus. Loss in the cation equivalent at anode is proportional to speed of cation mu. Loss in the cation equivalent to anode equal to Ku. Loss in anion equivalent of cathode proportional speed of anion V. Loss in anion equivalent of cathode Kb. Loss in cation equivalent at anode over loss in anion equivalent at cathode Ku over Kb. So U over V. Adding 1 on both sides, we get U plus V over V. Again, solving V over U plus V, loss around cathode over total loss equal to V over U plus V equal to T minus equation 4. Similarly, loss around anode over loss around anode plus loss around cathode, loss around anode over total loss U over U plus V T plus equation 5. From equation 4 and 5, it is concluded that loss in concentration of ions around the electrolyte is directly proportional to the transport number of ions moving away from it, which is called Retort's rule. Experimental determination of transport number. The transport number of ions are usually determined by following methods: Retort's methods, moving boundary method, EMF measurement methods. Retort's methods. In this method of determination of transport number is based on the Retort's rule. The rule states that fall in the concentration of ion around the electrode is directly proportional to the transport number of ion moving away from it. The experimental setup of Retort's apparatus is shown in the following figure. Apparatus and chemicals, anode and cathode, U-tube, the silver electrodes, voltmeter, and the AC-DC converter. Retort's apparatus consists of two vertical glass tubes connected by the narrow U-tube in the middle. All the three glass tubes are provided with stop clocks at the bottom to withdraw solution. The two side limbs are provided with electrodes which may be attackable. All the tubes are filled with solution under study. The two side tubes contain anode and cathode, which are anodic and cathodic compartment. The U-tube in the middle is called central compartment. We have to determine the transport number of silver or nitrate or standard silver nitrate is taken. The cell is connected in series battery and voltmeter for 2 to 3 hours by passing a current of 20 to 30 milliampere so as to produce appreciable change but not large change. After electrolysis, the solutions are withdrawn from each compartment, weighed and analyzed. There should be no change in the concentration of solution taken from the central compartment. The weight of the silver deposited on the cathode voltmeter is accurately determined. Calculation is first when the electrodes are unattackable. platinum electrodes are used. After electrolysis, let the weight of the anodic solution taken after electrolysis a gram, the amount of solute present in a gram solution b gram, weight of solvent a minus b gram, a minus b gram of solvent contain b gram of silver nitrate solution equal to b over 170 gram of equivalent of silver nitrate. So b over 170 gram equivalent of silver equal to y gram of equivalent of silver. Before electrolysis, weight of electrolytic solution taken before electrolysis C gram, fall in concentration C minus B gram of silver nitrate, C minus B over 170 gram equivalent of silver nitrate. Let weight of silver deposited in silver colorimeter be W1 gram equal to W1 over 108 gram of equivalent weight of silver, W gram of equivalent weight of silver. Transport number of silver fall in concentration around the anode in the gram equivalent over amount of silver deposited in gram equivalent. So TAG equal to D over W, and transport number of nitrate TNO3 1 minus D over W. Case second, when the electrodes are attackable, silver electrodes are used. Increasing concentration of anodic solution B minus C of silver nitrate, B minus C over 170 into 108 gram of silver. So B minus C over 170 gram equivalent weight of silver. If number of silver ion has migrated from anode, the increase in concentration of silver ions would have been equal to W. Fall in concentration due to migration of silver is W minus E. Hence, transport number of silver ion TAG plus equal to W minus E over W, and transport number of NO3 TNO3 1 minus E over W. Moving boundary methods. Apparatus consist of long tube fitted with the two electrodes at two opposite ends. Cathode electrodes consist with platinum and anode electrodes consist of cadmium. Hydrochloric acid solution fill at the top while the cadmium chloride at bottom. Hydrochloric acid is principal electrolyte, whereas the cadmium chloride solve is an indicator electrolyte, which enables formation of boundary due to difference in the refractive index or sharp boundary present between hydrochloric acid and cadmium chloride. Method: when a small amount of chlorine is passed through the conducting cell, the chloride ion moves towards anodes. Similarly, hydrogen ion as well as cadmium plus ions moves towards cathode, but the velocity of hydrogen ion is faster than cadmium plus ion. During electrolysis, H plus ions migrate towards the cathode negative electrode, where they undergoes reduction to hydrogen gas. The generated hydrogen gas is adsorbed onto the platinum foil cathode. Meanwhile, the cadmium plus 2 ions move slowly toward the cathode due to their lower mobility and may also be weakly adsorbed or influenced by the electrostatic interaction near the electrode surface. See, in case of moving boundary methods, two electrolytes are used, hydrochloric acid and cadmium chloride. The movement of migration of H plus and cadmium plus are different. The H plus ion is replaced by cadmium plus ion, and hence the boundary line makes in upward direction, that is the A, to BB. By measuring the length through which the boundary moves x equal to L, quantity of electricity is passed through the cell, the transport number of cation easily determined. Calculation: let concentration of H plus ion C gram equivalent per liter of solution equal to C over 1000 gram equivalent per ml. Let distance through which the boundary moves x equal to LC. Cross section area of tube is cm square. The number of equivalent of H plus ion moving upward is LC. Let number of the Faradays of current pass N equal to Q over F. Q quantity of current pass upon the Faraday. F Faraday fraction of current carried by S plus Ts plus multiply N. Number of equivalent of S plus ion cation moving upward. Faraday of current carried by cation. So that SLC equal to Ts plus N. Ts plus equal to SLC over N. C equal to C over 1000 gram equivalent per ml and N equal to Q over F. Ts plus equal to LCF over 1000 Q. S cross section area, L boundary length, C concentration of cation, F Faraday, Q quantity of electricity. Some application of conductance measurement: ionic product of water. Water is the weak electrolyte and it dissociates as the equilibrium constant of for above reaction is K equal to S plus OH minus over water. Since dissociation of water is very less, therefore water is constant. Ks2 equal to OH minus S plus. So Kw equal to OH minus S plus, where Kw is the ionic product of water. Step second, determination of degree of dissociation. At 25 degrees Celsius, the equivalent conductance of water K lambda Aq equal to Kb. K specific conductance of water 0.58 10 to the power minus 7 mole per cm. B volume of water in cc containing the 1 gram equivalent of water. Density of water at 25 degrees Celsius 0.9971 gram per cm cube. 1 mole of water, 1 gram equivalent of water, 18.01 gram. So density, mass over volume, 18.068 per cm cube. So lambda cube kb. The equivalent conductance of infinite dilution, we know the formula, lambda infinity S plus, lambda OS minus. The degree of dissociation, lambda equivalent over lambda infinity. Determination of ionic product of water. We know that Kw is plus OH minus. Let us calculate the S plus and OH minus. The mass of 1 liter water and the mass of 1 mole of water. Number of mole of water in liter. So S plus equal to OH minus. That is the C alpha. At 25 degrees Celsius, Kw is plus OH minus. Determination of solubility of sparingly soluble salt or saturated solution of sparingly soluble salts such as silver chloride, calcium sulfate is prepared in water of non-specific conductance Ks2, then specific conductance of salt K salt is measured. K equal to K salt plus K water, K salt K minus Ks2O. From the values of K salt equivalent, conductance of lambda of salt is determined. Lambda equal to 1000. K salt over C, C concentration of salts in equivalence per liter, that is the solubility. Since solution in dilute, lambda equal to lambda infinity, so lambda infinity equal to 1000, K salt over C. So C equal to 1000, K sal over lambda infinity solve. By putting the lambda infinity solve values in above equation, solubility of surrounding soluble salt can be determined. Determination of dissociation of weak acid. Consider a weak acid, ethanoic acid dissociate. So K equal to S plus CH3CO minus CH3CO, where alpha equal to lambda equivalent over lambda infinity. So lambda equivalent equal to conductometric titration, the titration in which the concentration of analyte is determined by seeing the change in the conductance at equivalent point. Strong acid, strong base, for example, hydrochloric acid and sodium hydroxide. Before the end point, hydrogen ion is replaced by the sodium ion due to mobility, and conductance decreases after the end point. Conductance increases due to OH minus mobility 199. Strong acid, weak base, ammonium hydroxide and hydrochloric acid produces ammonium chloride. Ammonium chloride also dissociates before the end point plus mobility 350 is replaced by the ammonium and the conductance decreases after the end point. Conductance becomes constant due to the common ion effect. Weak acid versus strong base, acetic acid and sodium hydroxide. Before the end point, S plus is replaced by the sodium, mobility 350 to 50, and conductance increases due to sodium ethanoate. After the end point, conductance increases due to hydroxide ion mobility. Weak acid versus weak base. The solution of weak acid has very few S plus ions, so initial conductance is very low. When the weak base, ammonium hydroxide, is added to it, more strong chloride. So ammonium ethanoate is formed and increased conductance. After the end point is reached, conductance remains almost constant because the free base, ammonium hydroxide, is a weak electrolyte. Precipitation titration, it is a type of titration which involves the formation of precipitate during the titration technique. In precipitation titration, the titrant reacts with the analyte and forms an insoluble substance called precipitate. It consumes till the less amount of analyte is consumed. Potassium chloride, silver nitrate, silver chloride. When silver nitrate added, the first part of the curve shows no increase in conductivity as there is only replaceable of chloride ions with nitrate ions. After the end point, conductivity increases because of the increase in concentration of silver as well as nitrate ions. Advantage of conductometric titration, it does not require indicators as titration, which is based on the conductance of solution and end point of neutralization point is determined graphically. It is suitable for colored solution as well as the end point is determined graphically. Results are more accurate with minimum error. It is used for analysis of turbid suspensions, weak acid with base mixture of weak and strong acids. Limitation of conductometric titration. By conductometric titration technique, only few redox titration can be carried out. It shows less accurate results when the total electrolytic concentration is high in solution. Electrochemical cell, the device producing electrical current from chemical reaction is called electrochemical cell. A combination of anode, cathode, and other materials arranged so that a product favored redox reaction can cause a current flow, or an electric current can cause a reactant favored redox reaction to occur. Electrolytic cell. An electrolytic cell can be defined as an electrochemical device that uses electrical energy to facilitate a non-spontaneous redox reaction. Electrolytic cells are electrochemical cells that can be used for the electrolysis of certain compounds. The apparatus in which electrolysis is done called electrolytic cell. For example, water can be subjected to electrolysis with the help of an electrolytic cell to form gaseous oxygen and gaseous hydrogen. Electrolytic cell. Galvanic cell, it is the device used to convert the chemical energy of reaction into electrical energy. Difference between galvanic cell and electrolytic cell. Galvanic cell, it is the device to convert chemical energy into electric energy, that is electrical energy produced due to redox reaction. In case of electrolytic cell, it is a device to convert electrical energy into chemical energy, that is electrical energy is supplied to electrolytic solution to bring redox reactions. It is based upon the redox reaction, which is spontaneous. It is redox reaction non-spontaneous. Two electrodes may be set up in solution of same or different electrolytes. Two solutions are set up in same electrolytic solution. The electrodes on which oxidation takes place is called anode, and the electrode on which reduction takes place is called cathode. The electrode which is connected to negative terminal of battery is called cathode, and the electrode connected to positive terminal The electrode which is connected to negative terminal of battery is called cathode, and the electrode connected to positive terminal of battery is called anode. In case of galvanic cell, salt base is used. In case of electrolytic cell, no salt base is used. Salt base. It is a U-shaped tube containing concentrated solution of electrolyte for Example, potassium chloride, potassium sulfate, ammonium nitrate, and agar-agar solution in 3:1 ratio, which have same transfer number or Hetero's number. It is a electrolyte which are required to complete the circuit in a galvanic cell. Working principle of electrolytic cell. It consists of compartment containing zinc sulfate and copper sulfate, dipping the zinc and copper rod respectively. These two electrosolutes are connected by salt bridge. Zinc and copper rods are connected with copper wire. Salt bridge contains potassium sulfate. Same transfer number helps to pass the ions from one compartment to other compartment without extensive mixing of two solutions. Zinc loses the electrons and copper gains the electrons. The zinc releases the electrons which passes into copper electrodes through the wire and gains copper plus ions to convert copper. This zinc electrodes dissolve in solution. The sulfate ions migrate one compartment to another and zinc plus vice versa through the salt bridge. Cell reaction, the change takes place by adding the half reactions, oxidation and reduction half taking place in the electrochemical cell is called cell reaction. Cell potential, the flow of current anode to cathode, that is electrical pressure, which is also called driving force or cell potential of cell. Half cell is half of the electrochemical cell. The half where the oxidation occurs and half where the reduction occurs is called half cell. Origin of single electrode potential, the tendency of metal to lose or gain electron is known as electrode potential. When it loses an electrode is called oxidation potential. When it gains electrode is called reduction potential. Notes found that whenever any metal plate is in contact with its ions, two phenomena are taking place simultaneously. The metal starts dissolving. The metal starts dissolving the ions goes in the solution and electrodes are shielding on plate. This tendency of metal to lose the electrons and ions go in the solution known as solution pressure of the metal, also known as de-electronation. When the metal is the contact with the metal ions, in this case, from the solution go and get the deposited on the surface of metal. In this reaction, the zinc ion gets electrons and produces zinc. This tendency of the ion of the solution to get deposited on the surface of the plate as a neutral product is known as osmotic pressure P naught of the solution concentration. If pH is greater than P net, it means solution pressure of the ions of the metal is greater than the solution pressure of the ions, that is the de-electronation. Phenomenon is greater than electronation. In that case, the metal will be having the negative and return left hand side of the cell, that is the anode. If pH is less than P naught, if the solution of pressure of metal ions lower, the metal tends to gain the electronation more than it loses de-electronation. Therefore, the metal acts as the cathode in the electrochemical cell and written as right hand side of the cell notation. If pH equal to P naught, it means that ability of losing and gaining the electrons in same for the metal in that case will not have polarity, that is the polarity 0. Such metal cannot be used as electrode in the electrochemical cell, also known as non-electrode. In this case, we have to understand the tendency metal to lose electrons, that is the PS. Outer metal, also de-electronation, and the tendency of ions of solution to get deposited surface when the metal in contact the metal ions, in case the cations from the solution go and get deposited on surface. The tendency of the ion, the solution to get deposited on the surface and metal. When the metal is contacting the metal ions, in this case, solution go and get deposited outside metal surface. The tendency of ions solution to get deposited on the surface is a neutral product known as osmotic pressure. That is the electronation. Osmotic pressure and solution pressure. So if solution pressure is greater than osmotic pressure, it is the anode that loses the electron and return left inside. If solution pressure is less than osmotic pressure, gain the electron and return is right inside, that is the cathode. If solution pressure and osmotic is equal, they are null electrodes and cannot be used in electrochemical cell. Standard EMF or cell. The EMF of cell determined under standard condition, 1 molar 25 degrees Celsius is called the standard EMF. The standard condition of standard EMF are 1 molar solution of the reactants in products, temperature at 25 degrees Celsius. Reference electrodes. The reference electrode is an electrode whose potential is arbitrarily taken as 0 or whose potential is exactly known. Primary reference electrodes. The standard hydrogen electrode is called primary reference electrode. The reference electrode whose potential is known as 0 as primary electrode. For example, standard hydrogen electrode. Standard hydrogen electrode can act as both cathode and anode. Hydrogen loses electrons as cathode, reduction, and gain the electrons. Standard hydrogen electrodes. Secondary reference electrodes, the electrodes whose potential is determined by connecting to the standard hydrogen electrode is called secondary reference electrodes. The reference electrodes whose potential is not 0 but exactly known, and the electrode's potential value depends on the concentration of solution in which it is deep. For example, calomel electrodes. When electrodes behaves as the anode, it loses the electrons and reacts with chloride, it forms calomel. In this case, fall in concentration of chloride ion when electrodes behaves as the cathode, reduction, and produces mercury. In this case, increase in concentration of chloride ion, so electrode is reversible with chloride ion. Electrode potential of calomel electrodes depends on if saturated potassium chloride is used, called saturated calomel electrodes. at 298 Kelvin, 0.2415 volt reduction potential. If potential chloride is taken as normal, these electrodes will be called as normal calomel electrodes at 298 Kelvin, reduction potential 0.280 volt. Nernst equation in electrochemistry, the Nernst equation is an equation which can be used to determine the equilibrium reduction potential of half shell in electrochemical cell. Derivation of Nernst equation consider general cell reaction A plus BB CC plus DD reactants products from Van 't Hoff's isotome for a reaction. Delta G gives free energy, K is the equilibrium constant, A is the activity component. At standard state, the activities of all the reactants and products are unity. So delta G naught equal to minus RT ln K. Delta G equal to delta G naught plus RT ln A product over A reactant. The free energy change is related to EMF of the cell. Delta G equal to minus N of E. Delta G naught minus NF E naught, where E and E naught are the EMF of the cell at certain concentration in the standard state. F Faraday of electricity, substituting the value of delta G naught in equation 1, minus NF E naught equal to minus RT ln K. So E naught equal to RT over NF ln K. Substituting the value of delta G and delta G naught in equation 2, minus NF equal to minus NF E naught plus RT ln A product of A reactant, dividing by minus NF on both sides, E equal to E naught minus RT by NF ln A product of A reactant. If activity A is replaced by molar activity C, E equal to E naught minus RT NF ln C product C reactant, equation 4 and 5 are Nernst equation. Alternatively, Mn plus Ne it gives M, and the Nernst equation is applied equal to E naught minus RT over NF ln AM over AMN plus the quantity of pure solid is arbitrarily taken as 1. So equation 1 becomes E equal to E naught minus RT over NF ln 1 over AMN plus. For very dilute solution, activity of solution is nearly equal to molar concentration. So relation 2 becomes E equal to E naught minus RT over NF ln over 1 over MN plus E equal to E naught minus 2.303 RT over NF log 1 over Mn plus at 25 degrees Celsius 2.303 RT over NF equal to 0.0591 over N. So E equal to E naught minus 0.591 over N log 1 over Mn plus at 25 degrees Celsius. Standard electrode potential, electrode is immersed into its electrolyte solution of 1 molar concentration, 1 atmospheric pressure of gas electrode at 25 degrees Celsius. Then the potential developed at the junction of electrode-electrolyte interface is called standard electrode potential and denoted by E naught. The absolute value of single electrode potential cannot be measured because oxidation half reaction or reduction half reaction cannot take place alone. Hence, the electrode whose standard potential Standard electrode potential is to measured to couple with some reference electrodes such as standard hydrogen electrode or calomel electrodes. Out of two electrodes, electrodes having the lower reduction potential acts as anodes and electrodes having the higher reduction potential acts as cathodes. If standard hydrogen electrodes act as anode, half cell oxygen takes place, half S2 gram 1 atmosphere. If standard hydrogen electrodes act as cathode, half cell reaction takes place. The standard EMF of the electrode is calculated by the following relation. Inert cell equal to inert cathode minus inert anode. If the standard hydrogen electrode acts as anode, inert cell equal to inert anode. If standard hydrogen electrode acts as cathode, inert cell equal to inert cathode. Electrochemical series. When electrons, metals of and non-metals in contact with their ions and arrange on the basis of values of their standard reduction or standard oxidation potential, the resulting series is called electrochemical or electromotive or activity series of elements. Elements, the standard reduction potential, lithium. Lithium have the lowest standard electron reduction potential. Fluorine have the highest, plus 2.87. Representation of electrochemical cell according to IPC, following the convention are used in the representing the cell on paper. Anode, it is written on the left and the cathode on the right. Double vertical lines indicates salt bridge or porous spot to eliminate liquid junction potential. Single vertical line represents the phase boundary. See, this is the phase boundary. This is the salt bridge. Anode is written in left hand side and cathode on the right hand sides. E equal to AR over EL. EL and AR are the reduction potential of left and right electrodes. The EMF of a cell determined under the standard condition 1 molar 25 degrees Celsius is called the standard EMF of the cell. The standard condition are 1 molar solution of reactants and products, temperature at 25 degrees Celsius. Calculation or equilibrium constant of a cell reaction from the standard EMF of cell. Let zinc plus copper reacts is the product Zn plus in copper is metal, copper is reduced and zinc is oxidized. So Kc equal to Zn plus 2 copper, Zn Cu plus 2. If Zn Cu equal to 1, Kc equal to Zn plus 2 copper plus 2. From Nernst equation, is cell equal to inert cell. At equilibrium, is cell equal to 0. So inert cell equal to minus 0.059 over n log Kc. In solving, inert cell equal to 0.0591 over n log Kc. Again, taking log Kc equal to an inert cell over 0.0591. Potentiometer for measurement of EMF of a cell. It is the device used to measure the potential difference accurately. Principle, it is based on the fact that potential drop in a wire of the uniform resistance is directly proportional to its length, B proportional L. According to Ohm's law, B equal to IR, R equal to rho L by A, so that B equal to I, rho L by A, so that B proportional L is a constant current flow through a wire using the uniform area. Figure potentiometer. Application of electrochemical series, prediction of anode and cathode. The electrode with lower reduction potential acts as anode, whereas the electrode with higher reduction potential acts as cathode in electrochemical series. Displacement of one species by order higher reduction potential, metal displays lower reduction potential. Example, copper 0.34 is displaced by zinc minus 0.776. Standard EMF of cell inert is calculated by the formula E cell equal to E cathode minus E anode. EMF of the cell carries out to be positive. The reaction is feasible, spontaneous, otherwise the reaction is non-spontaneous. Application of EMF measurement, determination of pH using glass electrodes. By applying the direct potentiometry, pH of the solution can be measured experimentally. In 1990, a biochemist Sorensen defined the pH as the negative log of hydrogen ion concentration. pH equal to minus log S plus molar concentration of S plus. According to Nernst equation, voltage of cell is linear to S plus concentration. In 1994, it was realized that electrode potential reflects activities of S plus rather than concentration. He again defined pH equal to minus log S plus equal to minus log S plus F S plus, where F S plus is the activity coefficient. The glass electrode is immersed into a test solution along with the external reference electrode. A tiny fiber soaks up with the solution, allows a very slow flow of electrolyte through the junction. The cell can be represented as the change in the cell voltage reflects the change in the test solution. The liquid junction potential EJ is small enough to neglect the voltage of cell flows. The relation is cell equal to K plus 0.0592 PS at 25 degrees Celsius. When the test solution is standard buffers whose pH is assumed as PSS. So ES equal to K plus 0.0592 PSS. So PSS equal to ES minus K over 0.0592. When the test solution is unknown, PS equal to U equal to K equal to 0.0592 PSU. PSU equal to U minus K over 0.0592. Substituting equation 3 from equation 4, PSU minus PSS, we can get PSU equal to PSS plus U minus ES over 0.0592. Determination of pH using the quinhydron electrode. Quinhydron electrode is commonly used electrode in the laboratory to measure the pH value of solution. Quinhydron is equimolar solution of quinone and hydroquinone. In acidic solution, quinhydron is strongly soluble and decomposed to give the quinone and hydroquinone. The electrode potential of source electrode is given by EQ over S2Q equal to inert Q over S2Q minus RT over 2F ln 1 over H plus Q squared. At 25 degrees Celsius, inert Q over S2Q equal to 0.698 volt reduction potential value, so that EQ over S2Q equal to 0.698 plus RT over 2R ln S plus squared. So we get EQ over S2Q equal to 0.698 plus 2.303 RT over half log S plus. At 25 degrees Celsius, EQ over S2Q equal to 0.698 plus 0.059 log S plus. So EQ over S2Q equal to 0.698 minus 0.059 pH. Equation 4 gives the single electrolyte potential value of quin hydrogen electrode. For measurement of pH, quin hydrogen electrode is coupled with the same reference electrode, saturated calamine electrode. The standard reduction potential value of saturated calamine electrode is plus 0.2420. In such combination, standard calamine electrode acts as anode and quin hydrogen electrode acts as cathode. Platinum wire or carbon is immersed into quin hydrogen solution to measure the conductance. Cell notation of quin hydrogen electrode is coupled with this saturated calamine electrode. The EMF of cell is given by is cell equal to ER minus EL. So EQ over S2Q minus E standard calamine electrode. Determination of pH by using antimony electrode. If extreme accuracy is not required for the measurement of pH, antimony electrode can be used. Glass electrodes are extremely fragile, that is easily broken, and if the accurate measurement of pH is not required, then antimony electrodes can be used instead of glass electrodes. When antimony electrode is dipped into a aqueous solution, then a thin layer of antimony third oxide is formed on the surface of antimony. This antimony third oxide is reversible to hydrogen ions of the solution, and hence pH measuring is feasible. The electrode reaction of antimony electrode takes place. The standard electrode potential of antimony oxide electrodes depends upon the surface characteristic and crystalline structure of antimony electrodes. Hence, the standard electrode potential of antimony oxide electrode is determined by dipping the electrode into a solution having the known pH. Potentiometric titration, it is the volumetric method in which the potential between two electrodes is measured. Reference and indicator electrodes is the function of the added reagent volume. Is cell equal to E indicator minus E reference plus EJ. EJ is the potential of junction potential. A graph of EMF versus the volume titrant added is plotted, and equivalence of the reaction is halfway between the sudden change in voltage. In the graph of delta E over delta V versus the volume of the alkali added is plotted, the peak of the curve signifies the EMF, the equivalence point. The graph is often called derivative value. Advantage of potentiometric titration. No indicator is required for potentiometric titration. Colored solution can be titrated by potentiometric titration. Indicators cannot be used for ordinary titration when the solutions are colored. In this condition, equivalence point is determined by the potentiometric titration. In ordinary titration, of prior information about relative strength of acid and base is required to choose the indicator. No such prior information is required in potentiometric titration. Titration of polybasic acids such as phosphoric acid can be carried out by potentiometric method. Such types of titration cannot be carried by indicator methods. More than one component may be titrated in the mixture of solution. For example, iodide in bromide may be titrated together. Why does the cell EMF change rapidly near the endpoint of potentiometric titration? In a potentiometric titration, suppose of acid and base titration, the indicator electrodes used in the glass electrodes and reflex electrodes in the calamine electrode. The EMF of the cell depends on the pH of the solution according to following equation: E equal E naught plus 0.0591 pH. During the titration, volume of alkali is added, and according to change, the pH EMF changes. At the beginning of pH or EMF increases slowly, but near the end point, as NaOH is added, pH increases abruptly and hence EMF changes sharply. After the end point, pH of the solution increases slightly and adding excess NaOH. Unselective electrode. Unselective electrode is an analytical technique used to determine the activity of ions in aqueous solution by measuring the electrical potential. Principle, it is the electrochemical sensor that works based on the principle of the galvanic cell. It converts the activity or concentration of the specific ion present in a solution into electrochemical potential. Working of ion selective electrodes, the working process of potentiometric ion selective electrodes is based on the principle of galvanic cell. It contains reference electrodes, ion selective membranes, and voltmeter. The transport of ions from the high concentration through the selective membrane creates a potential difference. It can be measured with respect to a standard reference electrode having a constant electrode potential. Under the equilibrium condition, the measured potential E can be expressed by Nernst equation. E cell equal to E naught plus 0.059 over n log a m n plus at 25 degrees Celsius, where n is the charge on the inlet ion, E naught asymmetric potential. Glass electrodes. A glass electrode is a type of ion selective electrodes where a thin bulb shaped glass membrane is used as the sensing material. It is sensitive to hydrogen ions in the solution. A carbon dioxide sensitive electrode is a pH sensitive glass electrode which is useful for analysis of carbon dioxide in water. Enzyme electrodes. Enzyme electrodes are the based on the principle where the enzymes can interact with the substrates in biological process. It is used to biotechnology and clinical analysis. Solid state membrane electrodes. It is a crystalline or solid state membrane electrodes containing an insoluble inorganic salts. Crystalline electrodes have good selectivity. An ion exchange process leads to the formation of potential at the membrane of crystalline electrodes. For example, silver chloride, silver sulfide can be used to determine the activity or concentration of changes ions. And exchange electrodes are based on the membrane which is electrically conductive. An ion exchange membrane is a type of organic polymer or ion exchange resin that transport specific dissolved ions from the solution and blocks other ions or neutral molecules. For example, proton exchange membranes are used to transport S plus ions. Anion exchange membranes are used in the certain alkaline fuel cell to transport hydroxide ions from the dissolved solution. Advantage of ion selective electrodes, it is relatively inexpensive and easy to operate. It is particularly useful in biological medical application due to ion selective electrode measure activity instead of concentration. It is a wide concentration measurement range. It is a real-time measurement which means it can monitor the change of the activity ion with time. It can determine both positively and negatively charged ions. Okay, it's all about electrochemistry under BSc second year chemistry, Institute of Science and Technology. Best of luck for your exam. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for your patience. That is now. Bye bye. See you again.